All right, guys, welcome to another episode of Cuda Education. We are continuing on our path, our clean slate path. We already did part one in the previous video, so this video now, I guess this will be clean slate 1.3. We are continuing with the view. This is step 2. This is view controller.m, the implementation. So again, just for you guys that are new to the whole series, this is a clean slate series, and you could see that based on the title of the video and the numbering system. So we are now continuing on the path of the second, I guess, step in the process of going from a very brand new, fresh, blank Xcode project that's created to an advanced modern renderer example that is freely available in the Apple Meadow sample code library. So we're building up to that, but we're starting from a blank, fresh project in Xcode. All right, so we're in the second step in this 16-part series. Obviously, there's going to be more steps, but we just have 16 parts, 16 steps for now, and we're just focusing on getting ahead. The first video was creating a blank screen with a navy blue background, and now we are continuing on this path. All right, so we are now in view controller.m. So that's this file, that's the main file. We were previously in the header file, and just real quickly, the header file, we changed, we had this simple thing in the header file to, we had a Cocoa metal and metal kit import, and then we also had the MTK view delegate, which we discussed in the previous video. So if you missed that part, you could go back to that video and see. So we're in view controller.m. That is the the main file, the view controller main file under clean renderer. All right, so now in this implementation, we see we have this view did load function, and in the blank project we had view did load, and we just had this piece right here. But in the updated the modification, we have all of these additions to it, which we will eventually get into, right? So we changed the blank project to this project because we're updating the project and everything. Okay, so we are in the view controller main file, and 3 instance variables. These are the minimum metal objects you need. So we have the device, the command Q, and the MTK view. All right, so device, command Q, and MTK view. So these are now variables that we could actually use in our instructions to do stuff. We have the GPU, which is this device thing. We have the command Q, which again, the command Q is when we want to the command queue is when we want to line up tasks for the GPU to do. And we have our MTK view, which is sort of the window and everything that we are trying to do. So we have these 3 variables initialized now, and of course that's all possible because in the header file we imported metal and the metal kit, which gives us the Apple Metal API in order to actually do this stuff. Okay, but let's stay focused. So we have our variables here initialize. 3 instance variables. These are the minimum metal objects you need. Device represents the GPU. Every metal object, buffers, textures, pipelines is created through the device. You typically create one at startup and keep it for the app's lifetime. So pretty simple. Command queue, a serial queue of command buffers to submit to the GPU. You also create one at startup and reuse it. each frame you ask it for a fresh command buffer. Each frame you ask it for a fresh command buffer. So, right. So each frame has a fresh command buffer. Okay, and then MTK view, a typed reference to our view, so we don't have to cast self.view every frame. So this is kind of, in simple terms, it's just the window that we render stuff and we draw stuff and what we actually see as our results for, the for our efforts in this whole computer graphics application. All right, so that's MTK view. So view did loan one-time setup. So this is view did load. We have a create metal device thing going on, a create command queue thing going on, and a configure MTK view. All right. So that's all of this right here, which is highlighting the change. So we could just dissect this for a second. We notice that we are using our variables. So we use the device, the command queue, and the MTK view variable, right? And we use it to manipulate and do exactly what we want to do. So what is it that we want to do? The order matters here. MTL create system default device. That's this function right here. This is the entry point to Metal. It returns the default GPU. On a Mac with integrated plus discrete GPUs, it picks the best one. All right, so obviously it's going to pick a GPU that, you know, Metal can run on. Again, guys, this is running Metal 4. Metal 4 can only run on M series chips. So you have to have an Apple M chip on your Mac OS system in order to run it, run the sample and run, you know, what we're doing here. For regular Metal, Apple Metal, there's Apple Metal and Apple Metal 4. For regular Metal, I believe, you know, you could have other like an Intel chip and stuff, but we're focused on the latest and greatest, mainly because it's just a matter of, you know, trying to buffer yourself against time. Okay, so we have, so that's the MTL create system default device, right? That's this function. So this function now assigns, it gets the GPU and assigns it to our underscore device variable. All right. So then now we have device new command queue. Right, this thing right here, device new command queue. Creates the command queue. Think of it as a conveyor belt to the GPU. You put command buffers on it and the GPU processes them in order. Okay, so like I mentioned briefly in the last video, we're actually seeing now, we're creating a variable that actually holds the command queue that's going to interface with the GPU to submit tasks and all that stuff, right? So we're now creating the command queue. All right, configure, number 3, configure the MTK view. The storyboard created our view as an MTK view. More on that below. So we can cast self.view to access the Metal Kit API. We give it a device, right? We give it a device, a clear color, and a delegate. So the device is basically the GPU device. That's easy. The clear color is a very dark blue output that we see in our window. So, you know, if you run the application, you basically just see a dark blue background, and I guess it's opaque, right? This is the color Metal fills the frame buffer with at the start of each render pass, right? So it's sort of the when you're clearing the screen, if you will, this is what is going to show up as sort of the background, the clear color thing. Yeah. And then the delegate, right? So the delegate self tells the the view call my draw in MTK view every frame. So we will get into the draw in MTK view thing later on, but it's basically saying, okay, you have this window, and obviously the window is basically representing what's coming, you know, what the GPU is doing and all of that, and it has a clear color, right? And then, you know, you're basically telling the delegate, listen, call my draw in MTK view every frame. So, you know, frames per second, 30 frames per second, 60 frames per second, every frame you're going to call the draw in MTK view. Okay, and that's what this thing is. That's what this thing is. That's all of viewed, did load. All of this is what's happening here. So we have our device, our command queue, and some information for configuring the MTK view, which is sort of our window. All right. I guess I'll just quickly go into the draw in MTK view. Yeah, so let's just quickly go through this, and then I'll stop. It is a lot of stuff though, but that's all right. All right, so draw in MTK view. Called every frame, 60 frames per second. You guys like 60 frames per second. I think 30 frames suffices, but we're in modern times now. The minimum now is 60 frames, okay? And we could see here that the update showed a bunch of things going on. So we're going to plow through this and figure out exactly what is what and what's happening. This is the Meadow render loop in its simplest form. Every frame. View. Let's see. View current render pass. View.current render pass descriptor. MTK view creates this for you. Okay? It contains the clear color and a reference to the current drawable texture. The backbuffer you will present to the screen. If the view isn't ready, example minimize, this returns nil, so we bill. So let's investigate this again. So MTKQ creates this. It contains a clear color and a reference to the current drawable texture. The backbuffer that you will present to the screen. If the view isn't ready, example minimize, it returns nil, so we bill. So what is the description here? Get the render pass descriptor contains the clear color. Okay, so that's what this view.current render pass descriptor is. Okay, and if not render pass descriptor, return. All right, so that basically means like if it's minimized, we're not going to do anything with it. All right, let's move on. The Q command buffer. Command Q command buffer. Command Q command buffer. Create a command buffer and render command encoder. Okay, get a fresh command buffer. This is a container for all the GPU commands in this frame. All right, so all the GPU commands are going to be in this variable. Render command encoder with descriptor. Render command encoder with descriptor. This is the key line. Creating the encoder with the render pass descriptor triggers the load action, which by default is clear. So just by creating the encoder, Meadow clears the frame buffer to our dark blue. In later steps, we'll insert actual draw calls between creating the encoder and ending it. Right, so I have seen this before in the previous videos that we have I've done on Apple Metal, where you start encoding and end encoding, and then you do a bunch of stuff in the middle. Right, so once you start the encoder, basically you get your clear color window thing, and then it clears the frame buffer to our dark blue. In later steps, we'll insert actual draw calls between the encoder and ending encoder, the starting encoder and ending encoder. So you get the starting encoder and the ending encoder, so you get stuff on your screen. Okay. So create a command buffer and render command encoder. Okay, so command buffer and render command encoder, I guess it's close cousins. They're sort of together, right? And we'll leave it at that for now. All right. Encoder end encoding finalizes the render pass. Nothing more to encode. Nothing to draw yet. The encoder just clears the frame buffer. All right. So we're done with this. So all of this right here is together. As you can see here, this is part of number 5. Okay. Present drawable plus commit. So present drawable and then commit. So we're down to this guy right here. All right. Tells the GPU, when you're done rendering, swap this buffer to the screen and then submit the whole command buffer to the GPU. All right, I've seen this before. I've seen this before in Vulkan, and just to give you guys a little context, both Apple Metal and Vulkan, which is another, I would say more of an open source computer graphics framework. They're both spawned from an API called Mantle, and Mantle was created by AMD, and it's sort of the start, the great ancestor to modern computer graphics in a lot of respects, because it spawned Vulkan, which is the successor to OpenGL. And it spawned Apple Metal, right? Apple literally took Mantle and then, did its thing to create Apple Metal. So this present drawable tells the GPU, when you're done rendering, swap this buffer to the screen and then submit the whole command buffer to the GPU. So like in Vulkan, there's this thing called a swap chain, which is basically, a lineup of frames that eventually is presented to the screen and blah, blah, blah. So I believe this situation right here, present drawable, is a similar thing. Tells the GPU, when you're done rendering, which means when you're done drawing on the frame. So think of the frame as like a painting, and you're drawing on the painting, right? Once you're done drawing on the painting and you have your final picture that you want to present to the world. So when you're done rendering, swap this buffer to the screen. So basically push it to the screen so that it can be presented to the world, and then submit the whole command buffer to the GPU. That part is kind of confusing, but basically you're committing, I guess you're committing all these instructions to the GPU, right? But we'll get into this commit thing, I'm sure, at a later date, right? But basically this line is saying, once you finish drawing, submit it to the screen, and then submit the whole set of instructions to the GPU so the GPU can process it. All right, but let's stop right here for today, and not get too overwhelmed. So yeah, guys, digest this stuff. It's sort of, you could take a picture of it, you could submit it to, APIs, to AI, and do your own research, and including, you could do the submit the code to your favorite AI, and dive deep into exactly what's going on if you have questions or what have you. But yeah, so just to recap real quick, what we did is we are in the we're in the view controller M file, right? So the main file for view controller, and we updated it with some variables. So now we actually have variables. We have a device, a command queue, and an MTK view variable, right? We initialized some variables, right? And we went through what those variables do. And then we did a view did load function, create the metal device. So now we not only initialize the variables, but we actually putting substance to the variables. So the variables now mean something. So the device holds now the GPU that's running metal. Command queue now, there is an actual variable with a command queue structure in it. And then we have some configuration instructions for the MTK view, right? And right, and you could see here, and here is exactly that. And then we investigated this draw in MTK function, which basically get the render pass descriptor, right? And that was right, and it tests to whether the window is actually viewable or it is whether it's viewable or it's minimized. If it's minimized, then it just returns. It doesn't do anything, because obviously if the window is minimized, there's no reason to be trying to do stuff. And then we have create the command buffer and the render command encoder. So we start the encoder here, we end the encoder here, and then what will happen in the future is that we will put instructions for what we want to draw, but we're not doing that yet. And we actually create the command buffer here. So let's see. Get a fresh command buffer. This is a container for all the GPU commands in the frame, right? So we get a fresh command buffer. So we have this variable now called command buffer. And we are then now notice that this command buffer is attached to the encoder, because we start encoding and then encoding. But remember, it's attached to this command buffer that's going to be used to, in the future, we're going to put instructions in the middle that's going to, actually do stuff, right? And then we have our render encoder. Right, it triggers a load action, which by default is clear. By creating clears the frame buffer down. In the later step, we'll insert actual draw calls between the encoder and the ending, right? So this guy, and then notice that we also reference the command buffer, right? So this and this, it's all part of the encoding. And then we present drawable to screen, and we commit the command buffer, right? So we commit all the instructions, right? So we shall investigate further, guys. We shall investigate further, but it's pretty interesting. One of the cool things I want to say is that one of the cool things about Apple Metal is that in the window, from what I understand, when the way how Apple Metal does stuff is that it will render something to the screen, and then it literally it will test to see if anything has changed. So let's say you're rendering a picture, you're playing a video game, and you pause the game, or you just stop for a second, and nothing in that in your window on your monitor is changing. From what I understand, what Apple Metal will do is simply just keep that frame. It will not keep refreshing the frame, and apparently that's because for processing and energy savings. That's kind of what I heard. I heard somebody say something like that, where it tests to see if anything has changed in the frame, and if nothing has changed, then it doesn't do anything. Okay, but with Vulkan, I don't believe that's the case. With Vulkan, it always refreshes regardless, which I don't know if it's a good thing or a bad thing. Don't quote me on it, but that's what I heard. So if you're looking at an energy savings perspective, then Metal does it differently. and I guess it's superior in that respect. But I'm not quite sure. I don't want to, I'm just telling you what I know, guys. Anyway, this is Cuda Education. Thank you for watching. We are slowly but surely making progress. It's the same, dark blue background, navy blue or dark blue background screen that we saw in the previous video. So there's nothing really to show here. Nothing has changed on the screen, but we are getting a better understanding of what's happening. I didn't intend for this video to be so long, but so be it. I prefer not for it not to be so long. But anyway, guys, feel free to take a picture of the code, submit it to your AI, and ask it questions and all that stuff. Thank you for watching. Have a great day.